welcome everyone to Monday night. This is our very first Ivan Hour here at ENC, and we're bound and determined to make this a tradition. Tonight, obviously, and then tomorrow night, Wednesday night. We have a very, very special guest with us tonight. In addition to being a longtime and very notable person in the NMR field, is also a very accomplished astronomer. And I'll ask Dave Rice, Ivan board member, to come up. Dave, if you'd like to make the official introduction.
Oh, okay.
And I'll back out of your way.
I've known Ron and Varian for years and years, and I've learned about his astronomy hobby and seen some incredible photos, and I think we're going to be seeing them tonight. And so, without further ado, I would say a night under the stars with resonating constellations to make it the NMR appropriate. So, take it away.
Thank you, Dave. Well, pressure. Really, this is a little bit of a story of personal experience in life, and it's also a bit of a story about history of us as a species and what we've learned about our cosmos around us here. So as the title says in the subtitles, I was shown a time machine by an amazing gentleman when I was a young child, and it changed me forever. No, let's see if does this work?
Press it just a couple times and it should go for you.
There we go. I can do it this way. Okay, testing 1, 2, 3. Okay, what this is not going to be about is terrestrial photography. But this is an image that I found incredibly beautiful and compelling. It was taken by an astro imager friend named Ivan Ong, who's the CEO of a chemistry company of all things, and knows and loves NMR. And he was in Singapore, and he was waiting for the moon to rise. So if you look in the image, what you'll see is back in here, the sky is brightening. So he was waiting for the moon to rise. And being an opportunistic person, he snapped this picture when these people just happened to walk out. So it was totally spontaneous. So astro imaging sometimes is spontaneous. Most of the time it is not, it is planned. This is what we're really going to talk about. We're going to talk about images that are taken with small telescopes from, in the most part, light polluted areas of my backyard. And now these days, I'm too lazy to go out into the deep unknown. So what we're looking at here is astounding to think about. It's an 8-inch reflector telescope. It's an image of a galaxy. And what we're seeing with the red jets that are coming out of there is literally the radiation in the low frequency bands that we can observe from a black hole that is eating stars for supper. So that is the radiation. This is what a black hole does. To give it some perspective, the distance from here to here is 10,000 light years. So speed of light, 7 times around the Earth in a second. Think about that. This is a scale that is unimaginable. So this is what we're going to talk about. So how did I get into doing this? So here I am at when I first started. There, they called me Lefty. And and probably the problem was I was an unruly child. I was in the 3rd grade, and today they would take me and give me Ritalin and calm me down and everything would be good. But back in those days, they said, let's find something for him to do. And so it was different. So I was about 8. This is the only texty slide there is, but it tells the story. There was a gentleman that in my hometown, his name was Michael Schottland. In 1937, he built an observatory in his backyard for the sum of $500,000 in 1937 dollars. He ordered a telescope. He had to wait 18 months for delivery. 6 months into the process, he got a call from this country of Mexico saying, I tell you what, if you allow us to take your instrument in the queue, we will refund. It was half down and half when you complete it. We will give you your $250,000, and then you'll take ours in the queue and you'll take it later. And his answer to them was, if I couldn't afford it and I didn't want it, I wouldn't have ordered it. So this is an unusual person when you consider 1937. So one of these instruments, which we'll show in person, is called Lonios. It's a very special kind of instrument. He gifted it to the Flagstaff National Observatory. And since then, it has been perhaps the most productive instrument on Earth for discovering dangerous near-Earth asteroids. So when I was 8 years old, I was taken to his house and he took me out into the observatory. I was stunned. Well, okay. Concepts about astroimaging. This is not what it's about. We're not looking through any eyepieces, whatever, blah, blah, blah. It's not the way it works. What we do is we hang a little sensor on the back of the telescope. And then we sit in a nice cool office in the summer or a nice warm office in the winter, or if it were clear in Texas with my iPhone, we could image from here right now in the observatory, which is really nice, ultra lazy. So this is an image taken with an 8-inch telescope, f4.7, focal length 953 millimeters. The sensor is 19 millimeters by 13 millimeters, and that's an object that most of us do know what it is. That is to put it into NMR jargon, that's a 50 microsecond acquisition of the moon. This is the same image scale, exact same instrument. The difference is now we're pointing somewhere where the moon is not. And this is an image that is probably about 4 hours of total acquisition time in various forms of the other. And in it, we've captured galaxies that are near and galaxies that are far. So the span of distance in the galaxies that are in this image is between, 25 light years and 100 light years distance in this little image. So that's the same field of view. But what we do know, if you think about it, is that the world turns. So this is an image with the same scale. And all that's happened is that the tracking has been turned off for 40 seconds. We live in a beautiful clockwork. Most of us know there's 360 degrees in a circle. Most of us know there's 24 hours in a day. So if you divide 24 into 360, you get 15. Okay, so it's 15 degrees per hour is how fast the stars advance across the sky. So in 1 minute, it's 15 arc minutes. In 1 second, it's 15 arc seconds. That's the distance. So in this amount of time of 40 seconds, these stars moved 10 arc minutes. The size of the moon is 30 arc minutes. And if you do remember, these dashes are roughly a third the diameter of that moon. So it's a clockwork. Okay. So when we start trying to image, we have to deal with this problem. So just like in NMR, if you got a supercon magneto-lock system, it's kind of optional, but it's nice most of the time. So just like that with imaging, this is Timmy. You have to name your telescopes. Okay. This is Timmy. This is the lock system. Down the back of here is a rotator and a focuser and a focal corrector, and the camera will go on the back of this. So this is the main instrument, if you will. On this, we put another small telescope, just like this. Here it is. Here is Timmy in the dome. Needless to say, the little red thing on the back is a camera. So with a 1 second exposure, that camera will capture 13 magnitude stars. And it can monitor the stars and say, are you where you're supposed to be? And if not, it'll issue a small micro correction to the mount. So as the mount tracks at sidereal rate, that's what we call the star rate in turning, that has to be corrected because it's not constant. You would think it's a constant clockwork, and it is, but we have this thing that we know and love called an atmosphere. At least we have it now. The lower you go into the atmosphere, the more the refraction. So as you change the angle through the sky, the sidereal rate changes subtle enough to utterly ruin these images. So you have to have some sort of a lock system. So that's Timmy with his lock system. This is Newt. Newt's the largest telescope. He's an 8-inch f4. So he's about that big around and about that long, and he weighs about 40 pounds. He's a big boy like that. Here's the lock system for Newt. The same camera, but now it's taken an off-axis pinch of light. The camera on the back here, this is a new addition. Oh, I'm not supposed to divulge it. I got a new camera. Things, in the home, anything that makes it from the front door to the observatory stays in the observatory. And so after a certain amount of time, when it is discovered in the observatory, you can truthfully answer that old thing. Right? So the camera has regulated cooling. Now, why do we do that? There's thermal noise with your imaging. We have all kinds of things to fight. The noise in the sky, the noise in your ears, the noise in the camera, the electronic noise. So in this land, for every 6 degrees centigrade you cool the camera, the noise is cut in half. So I typically image at about 35 degrees centigrade below ambient temperature. But that's not the good part. The good part is it's constant temperature. So when it's constant temperature, what it means you can do is you can take dark frames, which are images with no light, and you can build a library of those. And in every light frame you take, you subtract the dark frames. And the thermal noise of the camera goes away. And that allows us, with an 8-inch telescope, to get vastly deeper than the 200-inch Mount Palomar could do with film. Not even a contest.
Is that under vacuum, or how do you prevent condensation?
Oh, that's a dryer. It's sealed. The first line of defense.
Okay.
Now, basics. The bigger the telescope, the smaller the stars. Stars are point sources. They are so immensely distant that it wouldn't matter what image you look at. The bigger you make the telescope to improve the resolution, all that happens is the stars get smaller and smaller and smaller and smaller. That's what happens. They are not extended objects, okay? Now, the bigger the telescope, the smaller the region of the sky you can see for the same sensor, okay? The bigger the telescope, the more stars you can see. The number of stars you see is a function of the diameter, which is the light gathering. And the light gathering is just the area of the objective, okay? So here's an example of Timmy and Newt. I didn't bring Stella to the party. She's in between, she's angry. The blue box is the field of view from Newt, the longer focal length, 953 millimeters. Timmy is at 380 millimeters. So you see, you have much more field of view, but the cost is resolution. In this smaller area, you're going to see more and you'll get more detail, but it's a whole different word. So that's sort of the mechanics of astroimaging, okay? That's a little, I didn't even get into the real gory details, but this is an image with Timmy. This is not long. This is maybe 4 hours of exposure. We're pointing, it's galaxy season, in case you know. I'll get into more of that later. So we're pointing into the sky this time of year up. Nothing but galaxies. There are 3 galaxies. There are many more than that in here. These, distance-wise, they're 40 million light years away. So this is kind of what you can see, but if I change the telescope to Newt and just look at one of them, what you see is vastly more detail because the resolution of the optics is higher. You see more. There's little things that we're kind of at the noise level with the camera. It's a little bright, but that's okay, I mean, with the display. But this little trail that's running out there, that is a trail from a collision of a galaxy that ran through it and was consumed by this galaxy 3 billion years ago. And the remnant of it is still here, okay? Now, anyway, I already mentioned it. The area of the lens, the bigger it is, the more light. Your eyes, fully open if you're a youngster, is about 7 millimeters. That's as wide as they'll open. So you take that and compute the area, and you got 2 eyes, right? So we're NMR people, and what we know is that what you get out of that isn't twice, it's 1.4. It's the square root of 2 eyes. Now, if we had 9 eyes, then it'd be 3 times better, right? So Big Mike, who the telescope I saw when I was a kid, weighed 8 tons and was 32 inches diameter. So it captured 10,000 times more light than your eyes. That's the whole idea. Here's the big deal about astronomical imaging. You're always waiting for the stars. You're waiting and waiting and waiting, and they come. They're going to come. But unfortunately, these things appear. And when they are there, they are in the way. So what you end up doing is saying, I want to fool them. So this is the dome in the backyard. This is Donnie, the dome. And the device up here is a star sensor. Now, here's a homework assignment. When you all go home, how many of you have infrared cooking thermometers? Okay, a couple. Take your infrared cooking thermometer outside on a clear day, doesn't have to be night, and point it at the ground, and you'll see, oh, the temperature is, 75 degrees, unless you're in Texas. She'll say something else. Now point it up at the sky. It'll show you the temperature of the stratosphere. Isn't that cool? Isn't that cool? These wavelengths, these light, this energy, it just keeps propagating. That's why we can image galaxies that are 500 million light years away, okay? Same thing works with your infrared thermometer. So this can be used to tell an automation software, is it cloudy or not, right? There are other things. Next to the dome is a small dome. Cost me $5. It's a clear plastic dome. It's on a fruit cup, inside of which is a camera on double-sided tape. The dome is put on there with some sort of nice epoxy, some material to seal it from water. And then the whole thing is crammed into a really heavy mug that the handle fell off. You see, you can look online, you can say, I want an all-sky camera. And you can say, ooh, I can buy one of those. That's $2,000. Well, cost of goods here is $40, including the camera. It's been sitting in the yard for 2 years through tornadoes, hurricanes, thunderstorms, and the worst damage it suffered is the dog knocking it over. So with a camera like this, it takes an image every 30 seconds. So this is accessible to us here on my iPhone. So you can look and see, well, do you know, that's a clear night and that's a cloudy night. That big old globby thing over there, that's the moon. The moon is not your friend when you're an imager. Now, why bother to do this? Roberto Gil, if you get an email from Roberto, you might see this as a signature. And it's so true, right? The tragedy of life doesn't lie in not reaching your goal. The tragedy lies in not having a goal. It isn't a calamity to die without fulfilling dreams, but it is to not have any dreams, okay? So this is why you bother, okay? It's a matter of you're a small kid, somebody says, oh, isn't that amazing? You go home and you make telescopes out of Quaker Oat boxes and they don't send you off to the institution and here you are at the Ivan Suite. So this sort of thing is bizarre and it's wondrous. And it's all over the place. It's everywhere you point the telescope. It is every place. It's no difficulty finding targets. You will never get bored at finding targets to image. Never. And then you can always get a new camera and you got to do them again, right? Now, telescopes. Been around a long time. This is a refractor where, you know, everybody has one of these, one form or the other. So there's lenses at the front. There might be 2, 3, or 4 elements. Each one of these surfaces of these lenses has to be true across its diameter to better than 1/4 of a wavelength of light in order that it be diffraction limited. In other words, that the lens will perform sharply enough to do imaging. Like I say, the stars are infinitely small. They're not like taking pictures of us where we're, you know, big old guys, right? So this is a problem when you try to make it bigger. This is truly big. This is Yerkes near Chicago, probably. Where is this? Wisconsin? I don't know. It's a 40-inch telescope. It weighs multiple tons. People were thrilled to have it. And then they noticed a horrifying thing. When you point it up, the weight, the gravity causes the lens to distort. So this was literally the limit of how big you could make a refracting telescope. And this was heroic effort to do such a thing. You can see the building in the background where it would have to live. But fortunately, there are clever people. So in the 1660s, this guy named Newton did something, right? You know, Isaac Newton was pretty smart. He came up with this idea for a telescope. And the difference is the first surface of this mirror is what is silver, not the back. So this has only 2 optical surfaces. So it's much cheaper to make. And at slow focal ratios, f10, if you will, the figure is a spherical, so you can machine make them. You can produce them very cheaply. If you want to get faster than f10, they have to become parabolas, and that requires someone with real skill. But no matter what you do, the laws of optics prevail. If you're not true within 1/4 of a wavelength, it's not very good. So now there's more homework, don't you know? Reading list, The Perfect Machine by Ronald Florence. It's the story of the saga of building the Mount Palomar telescope, the Hale telescope. So you can get a sense of the scale of this if you've never been there. Those are people. The mirror is 17 feet in diameter. It weighs multiple tons. It was the first real serious use of Pyrex because it wouldn't have a heat figure distortion. When it was made, it took 4 years for the mirror to cool before they could figure it. It had to be cooled slowly so that it wouldn't crack. And then you started figuring it, and 12 years later, they were done. That's what was involved. Now you go, not even a lifetime later. This is the Webb telescope. I mean, if you believe what they tell us, it's out there. Here's Hubble, little less than 600 kilometers above Earth. Changed our knowledge of the universe drastically. So you're going to make something that's the size of Mount Palomar, and you're going to put it in orbit, and where you're going to put it, here's the moon. 1.5 million kilometers. It's at the second Lagrange point out. That's where it sits. This funny little wing on the back isn't a sail. It's a heat shield. So that's on the sun side. So this thing is, the camera's in it. I'm running at 10 below zero centigrade, and I'm thrilled and fat, dumb, and happy. Passively cooled, they're at 25 Kelvin. The camera's actively cooled 5 Kelvin. It's in orbit 3 times as far away as the moon. And it's up there now. It's astounding. Well, this is just about optical surfaces and what a quarter wavelength makes, blah, 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 blah. With Newt, to scale it up the size of the mirror to where that quarter wave is the thickness of a human hair, the mirror would have to be 550 feet in diameter. This is an 8-inch mirror. Mount Palomar was a 200-inch mirror. It was 1/10 wave. So you'd have to scale it up to 33,000 feet in diameter to be an error of 1 human hair. Webb, one of the segments, hexagonal segments of it, scaled to the size of the United States, but till you get a 2-inch error in the surface. So that's the kind of precision. So these machines are the most perfect machines that mankind has ever made. They truly are. They're wondering. Now we return to my story, and actually Big Mike's story. When they built Mount Palomar, I'm going to show some images in a minute. They made a survey telescope, 48-inch diameter, Schmidt camera. What does that mean? F ratio really fast. When you're taking images of extended objects, something like a nebula, pretty nebula, might look at those in a bit. It's an extended object. The only thing that matters there is the F ratio of the lens. The diameter of the telescope has no factor whatsoever. It's all about F ratio. This thing is F2. It's shockingly fast. So back in the day, that circle right there was where a piece of film would be put inside of the telescope. And they would expose plates and pull that out, and they would study that and say, oh, here's something nice to point the big one at. So the telescope that Big Mike paid $500,000 for is this today in Flagstaff. It's exactly this, but 1/2 size. And so, private citizen decides he wants one, crazy. Yeah.
And just the detector is that much more sensitive.
Well, its focal ratio is very fast. First off, it's approaching 1 meter in mirror. So its ability to record point sources like stars is outrageous. And give it a 10-second exposure and it's at 20-second magnitude. I mean, it's way, we'll look at what that means in a moment, okay? So, but it has wide field of view because it's big lens, but it's short ratio, focal ratio, so it can show a wide area. So this thing has discovered more near-Earth asteroids than any other instrument. And the people at Flagstaff had no clue where it came from. They had no clue. It had just always been there. And it ended up that the nephew of the great nephew of the gentleman who bought it, who are referred to as Big Mike, Michael Schotten, he was a software consultant and he was asked to do a job at Flagstaff. And he went out and looked at the facility and he saw this. He said, well, where's this? He said, nobody knows. They found the blueprints. On the blueprints, it had Michael Shotland's name and the latitude and longitude of the city it was made for, which was Martinsville, Virginia. So now Flagstaff knows. As soon as they found that, they named an asteroid for Michael Shotland. So there's now a Michael Shotland asteroid. And that's an interesting process because before you get an asteroid named for you, it's a long process. They have to study it for many, many years because they want to be really sure it's never going to hit Earth, right? They don't want to give anybody that honor. So I asked myself, I'm 8 years old with my cap gun, right? Gee, Mr. Shotland, why are you doing this? My feelings are he grew up in Russia. In 1908, when Tsunga hit, he would have heard it. He would have known about it. He would have heard it. It would have been in the news. Of course, 2013, there's yet another one. So there might have been that. About the time he immigrated to the United States was 1916. And what happened in 1916? This guy, this clever guy, published some rather interesting stuff. Okay? So he was quite interesting. So let's think about stars. Now, as a species, we've been at this a long time. So you think of stars as magnitude, and the bigger the number, the fainter the star. Okay? The faintest star you can see with your eye is 6th magnitude. There's 5,946 of those stars. From a dark location, those with really, really, really great vision might stretch to 7th magnitude. There's a little less than 18,000 stars. That's the total sum of what our instruments can show us. Okay? Every change in magnitude increases the number of stars by roughly a factor of 3 in time. It's a log 2.5 kind of scale. So today with my tech, like I referred to, the little red guide camera, 1 second exposure, I'm at 13th magnitude. So I have 10 million potential guide stars to pick from. So I don't have any problem wondering, well, there'll be a guide star there. Chances are there's something there to see. So the Greeks came up with this, 400 BC. They came up with the idea of a magnitude scale, where stars that were the first magnitude, the brightest, were 1, and then they delineated down to 6 magnitude. Or homework. Another must read. If you want to know a little bit about where we came from and what we know, a fantastic book, Coming of Age in the Milky Way. Lays it all out. There's a couple of interesting little stories here. Here's a picture of the full moon taken from Bovino, in Bovino, Italy, with a small lens, maybe, real short little camera, still in the patio, went click. Well, in the 1300s in India, they said, hey, if it's a quarter moon, it's kind of a special geometry in the relationship. They knew the world was round. It was not a question. They were a little brighter than we were. You have a geometry that's a right triangle. So people busily sat down and computed infinite series, which became what we call sine tables. And they determined in the 1300s that the sun is 400 times further away than the Earth. Look it up. It is not approximately right. It's exactly right. So this was in the 1300s. Okay. People are clever and they are resourceful. The thing that pulls it all together, one of my favorite songs. I don't know why. Do you know Sarah Bareilles? Gravity? Look at the poetry in this. Something always brings me back to you. It never takes too long. You hold me without touch. You keep me without chains. What a better definition of gravity. So, enter this clever guy, Newton again. In the 1660s, he came up with an equation, the relationship of mass and distance to gravity, to force of gravity. The problem was, nobody knew what G was. The gravitational constant was unknown. How are you going to do it? You didn't know the mass of the Earth. You didn't know the mass of the moon. You didn't know how far away they were. You couldn't compute it. So 100 years later, in Scotland, a minister geologist named John Mitchell, with the help of Henry Cavendish, they weighed a mountain. They were in Scotland, and in the next door to that, in the parlor of his home, he builds a big device and is hanged there with enormously heavy copper balls. So they knew the mass of these copper balls. And so the problem became, if we only knew the weight of the mountain, we could compute the gravitational constant. And so they weighed the mountain because the geologists knew that what the mountain was made of, and they knew what it weighed. In the process, they invented topographical maps. So they weighed the mountain and they came up with a gravitational constant by this method, by carefully measuring how much the copper ball leaned toward the mountain. They got it exactly right. It kind of humbles me when I try to integrate a spectrum. So like I say, it marches on. Where did it all come from? Well, yeah, it's still the same today. Okay, that's it. Redshift. Everyone stood by the railroad track waiting for the train to go by just so you get to hear the Doppler effect. I mean, hey, what fun is that? If you live in Colorado and the snow is quit, it's one of the most fun things ever to do. The trains come roaring by. So it's redshift. So it happens with the light too. Not just, it happens with any frequency. So if it's moving towards you, these lines shift to the blue. If it's moving away, they shift to the red. So one of the real drives to make large telescopes was that they had the resolving power to be able to resolve stars and distant things and do spectroscopy. So they could look at the line pattern in the spectroscopy and know, oh, that's lithium. And they could see how it shifted. And by how much it shifted, they know the blue shift and the red shift. That gives you the relative rates of velocity of is it coming towards you or is it going away? And so when Edwin Hubble and the boys did this in the 30s, everyone fell over. Because, for example, this is one of the galaxies they measured. This is Timmy's work. Timmy, look at this. This is a nice, modest galaxy called M101. He's racing away from us at 535,000 miles an hour. It's trucking. So they look somewhere else. But first, just looking at it, everything that's outlined in blue and red is another galaxy. And that's taken with a 3-inch telescope. If you point Newt at this, you see much, much more. And if you look at the image at actual digital resolution, I mean, this is just some barely average, I'm a barely average astro imager with this stuff. You see things that are remarkable. That little thing right there and that little thing right there, they are galaxies. And they are galaxies that are incredibly distant. The thing that we have to realize is that these are not nebulous objects. These are collections of stars. And the only reason they appear this way is because we cannot resolve the stars because the distances are so vast. When you went to the 200-inch Hale telescope, they began to be able to resolve the stars and do that. That's why you want a big telescope. You can do the science with it. Here's another neighbor. This one's really near. This is only 3 million light years away. This is racing towards us at 62,000 miles an hour. That's trucking. Now, why is that? So the reason is, this is what's pulling us. This is the only galaxy that you can see with your naked eye. In the fall, go out and look at Andromeda. You see the square of Pegasus and then Andromeda is flowing away. If you're in a dark place and look, you'll see what looks like a little smudge. It's about 8 full moons across. It isn't small. If you look at it in detail, what you'll see also is that there's a number of like little red glowing things. See those? See them? Look at this one again. Look, there's a strange red glowing thing. You know, what is that? What's going on? So let's point the telescope instead of pointing out into the cosmos. Let's point it at the next spiral arm out from where we are in the winter. This is Orion. This is the Orion Nebula. It's a star factory. It's an emission nebula. Its stars are being born and built here, and the energy is just going crazy, and it's causing the hydrogen to glow. in hydrogen alpha light. And that's the light, that's what we're seeing. So this nebula that's in our galaxy, we can see with a small telescope in imaging in distant galaxies. Here's another thing that people, it's a sort of an iconic image. Timmy, this is one with Timmy, because this is big. The Horsehead Nebula. As a visual astronomer, you see this image, you go, oh, I want to see that. I really want to see that. So you find somebody that's got a 20-inch telescope, and you go out some night and you look. You can't see a thing. It's too faint. You see this well, you see this. You see that, but you can't see that. But with a 3-inch telescope, we can image it beautifully. It's just a miracle. Here's another galaxy near us. It's really close, 31 million light years. It's up there right now, near the Big Dipper. Look at the handle of the Big Dipper. So it's a spiral galaxy. There's tremendous detail in it. We can still see nebulae, and there's this odd thing that's going on over there. What happened? This unfortunate guy ran through it a few billion years ago. That's why the arms are so bright. This stole all the hydrogen and gas, and it lit up with star making. So that's glowing with the light from the hydrogen that it stole from that galaxy. So that is M51, it's sort of an iconic one. Here's other interacting galaxies that are out there. This particular galaxy is interesting because its form and size is the same as our Milky Way. This is roughly what M31 and us are going to do. In about 5 million years, we're going to have a dance.
How far is that?
50 million light years, something like that. Yeah. Well, so what we see in the images we see are really a function of where are we looking. So here's like an edge-on galaxy. They're kind of cool. Now, what do you get for your $2.5 billion, if Hubble, if you will? Okay, this is Timmy, and he's trying his best to image M104, this galaxy up there. It's really a cute little galaxy. So I can look at that at actual digital resolution. You go, wow, look, I can see it. I can see the dust cloud on the front end. But for only $2.5 billion, you get that. So that's a Hubble image. And this isn't why Hubble is there. Hubble's there to look at other things. But the astounding thing is, at this kind of resolution, it can do spectroscopy on individual stars that are in that galaxy. This isn't the science camera. This is the pretty picture camera, if you will, for that. So, you got to pay for it sometime. So this is an image I took long ago of M1. This is the remnant of a supernova. Not just any supernova. In 1054, in England, there was a supernova. Was it in England? No, they wrote about it there. But the Chinese cataloged it really, really well. Star visible in the noonday sun for a month. What is this? Oh no. So this is the remnant of that. I found this data and I processed it in a way to show you what it would look like through like a 12-inch telescope if you were looking at it visually. So this is sort of what you would see visually in a large telescope, visual. This is Hubble. Now, when you look at this, it looks a bit like a high-speed photograph of an explosion, because that's exactly what it is. It's just that this explosion was in 1054, and this is what it looks like now. So the distances are undescribably vast in terms of light year size. So if you image this, even with my instrumentation, 10 years from now, I will have a measurably different object. As the supernova expands and expands, you see all of crazy stuff. And the little star, the neutron star that's in the middle is there. So what's a neutron star? It's a star that's collapsed. Its mass is enormous. It had an angular momentum from rotation. It blew up. It's got this enormous mass and it's compressed into a little tiny radius. Radius, I don't know how big it is. I think it's only like 100 yards or something. But it weighs like twice as much as our sun. So it turns at 50 times a second. So through a telescope optically, these are things that are fun to look at. Here's a globular cluster, stars, stars, stars. You think if you were there, you'd be overwhelmed by stars. You wouldn't. These stars, it's just from our point of view, right? They're still, the distances between them are still vast. So another globular cluster, M3. Other clusters, beautiful. I can't image them and show them to you like the delicacy that they are through an eyepiece, because your eye has far more dynamic range than does any sensor. You know, sensor can integrate for hours and weeks and days, or continuously and build signal, but your eye has a delicacy and a dynamic range we can't approach. So when you look in this, you see this little odd thing, and there's another one over here if you look close. What's that? It's a star like our sun that is gone poof. It's not supernova, but it's collapsed and its outer shells have blown out, like, way beyond the orbit of Pluto kind of things. And that's it glowing from the remnant sun. Okay. Double cluster, a beautiful kind of thing. But really, we have all kinds of things. This is, red things. This is the fox fur. It's in Monoceros near Orion. The cone there is a very iconic kind of image. Hubble took a photograph of that that's stunning. You can, in narrowband light, which we'll look at in a little bit, it's really, really a dynamic thing, but it's a star factory. All of this, new stars are being birthed and born and everything, and every so often one pops out. Blue things, they're reflection. They're not, the red things are emission. It's the energy of a sun makes the hydrogen emit hydrogen alpha radiation, and that's deep in the red or that. But the blue things are, there's bright sun, bright star and light, and there's dust and stuff, and it reflects it. So that's a blue thing. I like the blue things. They're scary things. If you turn this on edge and point it up, it's called the Witch Head Nebula. It's very scary. It's really a frightening thing. There's dragons. Okay. This is a hydrogen alpha image taken with Stella, who's angry that she wasn't introduced, the telescope. But just the diaphanous form of this and all the detail and the tendrils of this, nobody really knows exactly what's going on here, right? So what do you call it? The Dragon Nebula. Why not? That's a squid you don't want to meet. So when I did this image, I think I did it at an Ivan, I included it. I called the image Squid from Hell. And it's a massive red nebula. So this is taken in two wavelengths. It's taken in hydrogen alpha and oxygen 3. This is all oxygen 3, and you can see through it the red nebula behind it. And so to get that kind of contrast on it, I selectively stretched and masked the oxygen 3 wavelength to make it stand out. But it is very, very real, but the contrast is utterly fake, okay? They're blue and red things. They're far things. Here's a galaxy. It's 50 million light years away. We can see detail in it. We can see all kinds of little galaxies around here. The guiding is terrible in this. I was out, this was back in the days when I'm out in the wind in the mountains of North Carolina. It was totally delightful, until the bears come. Then it's different. Over here, that little gathering of galaxies is called Stephan's Quintet. It's 500 million light years away. And to think that with a $400 telescope, not particularly long, maybe 6 hours, maybe. But what's really made things different now is chemistry in the sky. So we can use sulfur, oxygen, and hydrogen emission filters. In this case, the bandpass is 6 nanometers of each. And you can point it at objects and separate it by the chemistry. So in this particular case, the blue is oxygen, ionized oxygen. The red is really a combination of sulfur and hydrogen. And then the hydrogen is what's remaining, mostly the green. It's mostly hydrogen. If you look at it in natural light, this will just look red, nothing but red. But by doing what's called the Hubble palette of using narrowband filters, you can get tremendous scientific information about the chemistry and things that are going on. Now, in our Milky Way in the summer, in the northern hemisphere, if you live in Australia, you're out of luck. There's Cygnus in the middle. So there's a bright star right in the middle of Cygnus called Satyr, named by the Arabs. They named almost all the stars we know. During the Dark Ages in Europe, when we were, food good, fire bad world, they were busily cataloging all the known stars in the universe in Arabia. Pretty dark there. This is a 6-panel mosaic in hydrogen alpha light, where that star there is Satyr. So we're just looking at that, and this is what you see in that area in our summer Milky Way, if you will. So you look at it and you go, oh, there's all kinds of cool stuff going on here. So you might ask yourself, well, what's going on in here? Or what's that all about? So you can enlist Newt and you can point him at that object and image it in the true Hubble palette, SHO. What that means, S. Sulfur is mapped to red, hydrogen is mapped to green, oxygen is mapped to blue, RGB. So that's what's in there, in that area. So if we point at the other little curious thing, the Crescent Nebula, this is mapped hydrogen, oxygen, oxygen. So hydrogen is mapped to red, oxygen is mapped to both green and blue. So this is very easy to do. What's nice about this is you can do this imaging from an apartment top in Manhattan. There's not a lot of hydrogen alpha light coming out of the street lights. And the narrower the bandpass, the better. So there's all kinds of cool detail and little things. So when you do the chemistry part and the narrowband imaging, you begin to see detail in objects that you can't, because here's a supernova remnant. Good, time's about right. This is the Veil, half of the Veil Nebula. It's mapped in HSO, which means hydrogen is mapped to red, sulfur to green, oxygen to blue. So I can change the palette and look at the chemistry in a different way. This is the remnant of a supernova, the other half of which is up there somewhere. It's another two other pieces that are just like this. It's immense in the sky. So this is a supernova remnant from long, long, long ago. It's still fluorescing, okay? This is energy that is still fluorescing from the supernova when it went off 3 billion years ago. Now, this is something in the summer Milky Way. It's not a good image, it's sort of ugly, but it's an SHO image. It's called the Tulip Nebula. And you see it sort of kind of looks like a tulip. But if you notice, there's this funny dark band shooting out here, and there's sort of a funny blue arc that's there. What's that? If you take the same data and process it for natural color, okay? So I'm processing HOO. You see the same filters. That's now in red and that's there. What this is, these things are a jet and a shock wave from the Cygnus X1 black hole that lives right here. The first black hole that was ever truly known. Can't see it, but you can sure see it's there. Okay. I just love the blue here. You know, it's just so nice, kind of like, you know, looks like clouds. It's really nice. Clouds get in the way. But by using narrowband, you can get all kinds of detail and see things that are not there. And light pollution doesn't bother you too much. Getting near the end here, location, location. This is an object, it's called the Dolphin Nebula. It's quite large. It's the same, this is the same size as the full moon. It's huge. It's located really low in the sky for us. Its declination is like minus 20 degrees. Okay, it's way, way to the south. So where I live in Texas, north of Dallas, I'm looking over the top of Big D. And so it's very low and you're looking through the atmosphere. And so it's very extinguished just from it. It's light mass, it's air mass. So if you're at 45 degrees versus straight up, you're looking through twice the air, you know, pretty much. So low, this was a heroic thing to image from Texas. This is 68 hours of data acquisition done over a long time. I didn't do it. I just told the scheduler program, if it's cleared, go after it, right? From South Africa, where it's straight up, you can do this in about 4 hours. Location, location. Look the other way into our winter Milky Way. Anywhere you look, there's clouds, there's scary things. And then there's the blue thing, one of my favorite things again, the emission. I just have to put him in there again. There it is. It's great. All kinds of cool stuff. These objects here that are red are 22nd magnitude. They're unbelievably faint objects like that. And with today's technology off the shelf, even a knucklehead can do it. Super faint, ABL 31. These are objects that what we're looking at now are stars that have died and they have outgassed. This is the fate of our sun. Our sun isn't massive enough to nova. It's just going to go poof. This is what will happen. This is very nearby. It is very large, but it has just happened. So it's not glowing brightly yet. It's just starting to grow. So this is a very, very faint object. And that little funny greenish star right there, that's the guilty party. That's the guy. Here's others. Same fate. Okay. That's happened much further away, but it happened a good long time ago. One of my favorites is this. Why do I like it? Looking through it, I don't have the detail to do it. I think I can do this now with far more resolution. That object there and that object there, they're spiral galaxies that are 500 million light years away, and they happen to be pointing through it. Okay. Here's one that anyone who's looked through a telescope will have looked at. M57, the Ring Nebula. What does this look like through a telescope? This is sort of falsely processed to show the galaxy that's out here and all that. But the bright area that's there is an incredibly elegant smoke ring. It looks like a little tiny smoke ring that Humphrey Bogart blew in a movie in the 40s. It's exactly what it looks like. So that is a remnant of a star. The helix, a much larger version of the same thing. I want to do this again as well, because there's detail in the tendrils that are pointing toward that star that I think I can capture now. When I did that 10 years ago, I didn't have a clue. And finally, another one I want to do, because I have a larger sensor and I can put it in context, much bigger thing. But this is in narrowband light, and you can see there's a lot going on. It's a lot of chemistry happening in the sky. But return to this. And the reason I showed this Sunday at the end of my talk at the Joel thing. Oh, by the way, I used a Joel Mach 1 telescope mount. Whoops. So this is 40 million light years away. This is 60 million light years away. And every one of these smudges are different kinds of galaxies. And if I put the software program on there to say, show me all the galaxies that are in this field and in this image, it shows over 100, there's over 130 galaxies in this field. So why this image? I'll repeat the line. It's galaxy season. If you go out now at midnight and look, there's no Milky Way. If you were in a ship in the middle of the ocean, this is really the last slide, I promise, then, and looked around you, you would see that the Milky Way is running right around the horizon. The Milky Way is our galaxy. So in the summer, in the northern hemisphere, we're looking into the core of our Milky Way. In the winter, where Orion and Perseus and all this stuff, that's looking into the next spiral arm out of our Milky Way. So it's like a disk. So as the year goes, that disk turns and it's now here. So now, anywhere you point a telescope, it's incredibly boring. There is nothing to see. But if you point an imager at it, there's galaxies anywhere you point. So visually, these are nothing but distant galaxies. But imaging-wise, it's incredibly exciting because anywhere you look, there are galaxies there. Looking into the winter Milky Way, there's something going on there. Kind of thing I can't image. It's not dark enough. Need a super dark site to do this well. I wouldn't even tell you how long this image is. But it's an attempt to capture the dark clouds and things that are there. Okay, I think I might be able to do better now. I have better read noise. A really compelling object called the Angel Nebula. And I want to do this with a larger telescope. Why? Larger telescope, if we remember, smaller stars. So this image is dominated by the stars because I was using a small telescope. But if I have a larger sensor, I can use a larger telescope and the result will be the stars will shrink and they won't dominate the image anymore and the angel will come out more. Okay. Just more wondrous chemistry in the sky. This does give you a sense of all of the dust and all of the busyness that's available. Now, the final slide here. This is Ricardo's sign-off guy, Benjamin Mays, a minister and educator, born 1894, died 1984. Essentially the same generation as Big Mike, the guy who had the telescope. When I asked his granddaughter, who I went to high school with, Purnell, I said, well, why did he do this? She says, I have no clue. But the kind of guy he was essentially the words that are here. In other words, every man and woman is born to do something unique and distinctive. And if you don't do it, it won't ever get done. That was his attitude about life. So that's why he acquired the observatory and the telescope. This image here is done by another artist friend. She's in Chapel Hill, North Carolina. She and I were on a volleyball team for years and years. So Catherine is a friend and an artist, and she does beautiful mosaic art. So this is the idea of that a creative person, you have no power over life. You are literally a slave to your passions. You're a captive and you're driven by it. And that's really what astroimaging passion is about for anyone who does it. You know, it's not a matter. So the image of doing it, I thought she captured it really well. There's this bird that's free and on the outside, and that's all of us, you know, but inside here you are, you're trying to push the hobby uphill all the way. So that's it. One thing to remember, That's why Stonehenge idea didn't stick. Okay, once daylight saving times came, you know, the Druids, they couldn't do it anymore. You know, it's a lot of work to shift that thing a little bit over like that. And we end where we began. Started with M82 and the jets from the black hole that are eating things at a prodigious rate, but we put it in context. It's not alone. Here's another galaxy, spiral, that is nearby, M81. All the nebula are there. And if you have binoculars this time of year, you can look and you can see these two for what they are. You can look with binoculars and you can see that is a spiral. It's, you know, it's phenomenal. But the world is beautiful. It depends on how you look at it. That's all it is. So thank you very much. I expect everyone to give me a book report tomorrow on the perfect machine. Yeah.
If I could. First, what can you tell us about the coloration? What can you tell us about the coloration? You mentioned some were natural color. So we're guessing, you know, some maybe enhanced color, but others that showed no color.
Well, what we do is I image with a monochrome camera because it has more resolution and more sensitivity. So I shoot for natural light. I shoot through a red filter, a green filter, and a blue filter. And then those get combined. And you also shoot through a luminance filter, which is nothing but all the bands. And that's where the detail is. So you can enhance the luminance for resolution and detail and pull out things and combine it with that. That's an LRGB kind of image. The other images that have the chemistry color, if you will, that is from narrowband filters. And it is totally free to map the colors any way you see fit. Because it's not about truth. It's about science in the sense of what chemistry is out there, not what it visually, truthfully impairs. Because visually, if you look at any of these things that are nebula, they're red. In other words, they are dominated by hydrogen and sulfur. They are red, purely. And so only when you break it into the narrow band do you, so you map those filters to any color channel you want and combine.
And then the second question I had, these, I'm guessing were all optical wavelength. And yeah. Where do other wavelengths come into the scheme, X-ray, IR, and so on?
Well, the Webb telescope, if you noticed, I didn't get into this, its mirror is gold. So it's a 17-foot diameter, it's hexagonal segments to make a 17-foot diameter mirror. Each of those segments is automatically controlled to make a perfect figure to within 1/5 of a wavelength of light. That's, and by the way, let's put it beyond Mars, but orbit it beyond the moon, right? Its coating is gold. Why gold? Gold is very, very reflective to the infrared. And if you want to look far, you have to look in the infrared. The longer wavelengths are simply killed by the dust. And the shorter wavelengths, the blues and stuff, they vanish in the dust, if you will, all the dust and debris in the universe. But if you go into infrared, those longer wavelengths propagate through the dust for a long way. So what Webb is really all about is looking way back, way back. Yeah.
Are there other questions for Ron? The microphone is yours.
Mm-hmm.
Thank you. Okay, I'm sorry I missed the first part of the talk. You probably talk about it, but I have a very naive question. So when you say like you have an exposure time of like 6 hours,
yeah.
Do you need to compensate for the like spin of the Earth to get the perfect picture of the galaxies and stars?
Yes.
Okay, so like how do you do that? Like there is a built-in mechanism for the telescope to do it, or you have to manually?
I can't quite hear with the echo. What?
I mean, just how do you compensate for the Earth's spin when you take the picture, like you exposure time is 6 hours, like,
Oh my. An individual subframe is, this is NMR, this is NMR imaging. This is astro imaging 101, and it's an important point. The read noise of the camera is measured in electrons. The camera I have now, its read noise is 1.2 electrons. Its quantum efficiency is 95%. So 95% of the photons that hit this sensor get turned into electrons that become electrical current that gets counted to make the image. Where this becomes important is the read noise of the chip. If I'm pointing it in the sky and it's a bright sky, there is no point in exposing longer than it takes to swamp the read noise of the sensor. In other words, if I need 60 hours of exposure to get an image, I might be doing it from a place to where going beyond 120 seconds is a foregone conclusion. I'm not going to improve it because of the brightness in the sky, right? So what you do is you take a lot of short frames and they all get co-added. But the mounting and the tracking is another technical matter. It's a machine. It just runs.
Yeah, okay. So let's thank Ron
Yep, my
for a
pleasure.
wonderful lecture.
Thank you.
And